Okay, so in the last video we learned how to take the derivative of a sum or a difference. Here we're going to take the derivative of a product, right? So we're going to take the derivative of a product of two things, let's call them u and v, right? Or if you prefer, say f of x times g of x. Either way, I'll write them both down, right? So first of all, because derivatives are limits, right? It's the limit of the difference quotient. You might just think that because you can take the limit of a product and the product of the limits, and they're the same, you might think that you can just multiply the derivative of u times the derivative of v. Right? Then that would be my guess, right? That seems to be okay, right? In other words, you can also do f prime times g prime. Right. But can we really do that? Is that the rule? So let's just see if that works, right? Let's do an example. Right. Suppose I want to take the derivative of, let's do the product x times x squared. Okay? Now, on the one hand, if you suspect that this rule is just to multiply the two derivatives, then we're going to take the derivative of x times the derivative of x squared. And what would that be? Well, the derivative of x is 1, right? And the derivative of x squared is 2x. And 1 times 2x is just 2x. Is that correct? No, of course not. So rather than try to do this rule here, how would you take the derivative of x times x squared? Well, what you should do is simplify, right? The derivative of x to the 1 times x to the 2 is x to the 1 plus 2. Just add the exponents, right? The derivative of x to the 1 plus 2 is x to the 3. So what we really should have done here was just take the derivative of x cubed, which we did many times. That's just 3x squared. So that's the answer, right? But that's not equal to 2x, right? So this does not work, right? So the product rule, while this would have been nice if it works, it's not that. You cannot just multiply the two derivatives. Okay? We tried it. It doesn't work for this example, and it doesn't work for almost all examples, right? So, now that we know what not to do, right, what is the actual product rule? Right. And I'm not going to derive it. I'm not going to prove it. I'm just going to write it down, right? So, if you're taking the derivative of u times v, here's what you have to do. You multiply u by itself times the derivative of v. So first times the derivative of the second. Then to that you have to add the following. You add the second, v, times the derivative of u. Okay? In terms of the more familiar f and g, right? This is going to be f times g prime plus g times f prime. Okay, so whichever way you want to remember it, right, these are the same. It's just two equivalent ways of doing it. Right, that's what you have to do here. Okay, so it's right. So the derivative of f times g first times the derivative of the second. So f for first. First times the derivative of the second plus the second times the derivative of the first. Right. So that's how I remembered it. First times derivative of the second plus second times the derivative of the first. Okay. Let's do an example. Well, let's do the one we just did. Right. Let's do the derivative of x times x squared. Now, of course, we know the answer, right? We got it by taking the derivative of x cubed, which was 3x squared. But now let's do it the awkward way of using the product rule here, right? So we can think of x, right, as my u, and then my x squared as my v. Right? So I'm going to default to this one here. Or you can think of x as f of x, and then x squared as g of x. But either way. Okay, so u is just x, right, and then times the derivative of v. So the derivative of v is the derivative of x squared, plus, right, v is x squared times the derivative of u, but u is just x, so the derivative of x. All right, so we still have to take the derivatives, right? This is just x, right? Don't take the derivative of x. We're taking the derivative of x squared, which of course we know is 2x, plus x squared times the derivative of x. Well, you should know the derivative of x, right? Dx over dx is just 1. Okay. So what do we get? We get 2x squared plus 1x squared, which of course is 3x squared. And of course, we already knew that, right? That was the answer. But now the product rule actually works here. This product rule is the one that works. Okay. We tried it the usual way, taking the product of the two derivatives, but that did not work. You have to take this combination. Okay. So, yeah. And unfortunately, there's not a whole lot of examples we can do right now that aren't sort of contrived, right? For example, we can take the derivative of, x to the 4th times x to the 6th using the product rule, but let's not use the product rule. Let's simplify, right? This is just x to the power 4 plus 6, which is x to the power 10. Now just use the power rule, right? 10x to the 9. And that's it. So if you want to use the product rule, right, you would do x to the 4th times the derivative of x to the 6, right, plus x to the 6 times the derivative, sorry, that's a 6, time, I made it worse, didn't I? Okay, so x to the 6 times the derivative of x to the 4. So x to the 4th times 6x to the 5 plus x to the 6 times 4x to the 3. So this would be 6x to the 9 plus 4x to the 6 plus 3 is also 9, right? And then 6x to the 9 plus 4x to the 9 is 10x to the 9. And you can see that this was not as pleasant as just simplifying first, right? So here's the overarching principle here. Before you take the derivative, simplify first. Right. It's usually easier than having to do it the long way without simplifying. Right. Simplify first. Right. If possible. In some cases, it's not possible. Right. If possible. So there you go, right? This is the product rule, and that's how to use it. So I'm going to do one more example, but in this example, we don't have a choice, right? We have to use the product rule. And maybe let me copy down the product rule, u times v. So u dv, oops, that's a v. Sloppy. There we go. U times the derivative of v plus v times the derivative of u. So the example I have in mind is the following. Suppose we want to find the derivative of x cubed, well, let's do x to the 4 times sine x. Okay. So can we simplify this? Not that I know of, right? X to the 4th times sine x. There's really nothing we can do here. These are just two functions, right? This is your u, and this is your v. So here, if we want to take the derivative, we have to use this product rule. There's no choice. So u is x to the fourth. Oh, what is the derivative of u? The derivative of x to the fourth is 4x cubed, right? And what's the derivative of v? The derivative of sine, well, I hope you know that by now. It's cosine, right? We did that in the last video. So now we have all the ingredients, right? Now we can write essentially u times dv. So u is x to the fourth, and then the derivative of v, which we did down here, right, is cosine of x, plus, and then v is just sine, sorry, that's a plus. V is sine of x, and then the derivative of u is this, right? That's the 4x cubed. Okay, and I didn't need this whole arrow here. Just messing that up. Anyways, so that's the derivative, but I think we can probably rewrite this a little bit nicer here. So this is going to be x to the 4 times the cosine of x. And then why don't I bring the 4x cubed in front times the sine of x. And that actually, that's probably good enough. Let me just write it a little bit better. X to the 4th cosine of x plus 4x cubed times the sine of x. That's good enough. You could, of course, factor out a factor of x cubed. So this will just be x times cosine of x plus 4 times sine of x. Right. You know, and I'm not sure that helps, but here's where it would help, right? Let's suppose you want to know where the tangent line is horizontal. Remember we did that last time? What would you do? You would set this equal to 0. And you would solve for x. And of course, one answer you would get right away is x equals 0. Then you would have to solve this part, which don't bother doing. That's a very hard problem. So maybe not for this example, but for other examples, you might want to factor things out. In this case, it doesn't matter. I would have accepted this, and I would have accepted this. We're not going to set it equal to 0 in this case, I don't think. Okay. All right, so that's the product rule. Very useful, and one that you really just have to get used to, right? Because it's very tempting to say, oh, the derivative of x to the 4th sine x, you know, if you're not careful, you might think that this is just 4x cubed times cosine of x. But we know that's wrong, right? You cannot just multiply the derivative of x to the 4th times the derivative of sine x. You simply get the wrong answer, right? You don't get the correct answer. Right? The correct answer is down here. Oh, you get 4x cubed, but it's times sine x. You get cosine of x, but it's times x to the 4th. You get the sum of two terms here. Here you just get one. So please don't do that, right? That's just the wrong answer. Right? So yeah, you have to get used to the product rule here. Right? In some cases, you can get around it by simplifying, but in this case, in this example down here, you had no choice but to use the product rule. Okay, so that's the product rule. What about the quotient rule? So there's also a quotient rule. And again, I'll just write it down. So let's suppose we're going to take the derivative of u divided by v. It's going to be v times the derivative of u minus u times the derivative of v, and then all divided by v squared. Okay. If you'd rather use f and g, I don't blame you. So let's say f of x divided by g of x. Then it's g comes first times the derivative of f minus f times the derivative of g, and then all divided by g of x, the whole thing squared, right? The function squared. Okay, and yep, it's you just have to get used to it. So one thing that's, well, someone taught me many years ago, but not original. Originally, I just memorized this. But if you don't mind yodeling, we have high, which is the numerator, and low is the denominator, high over low, right? So you just yodel. Low-d high minus high-d low over the square of what's below. So let me write that down, right? Low d high, right? D stands for derivative, minus high d low over the square of what's below. So if this is what helps you remember the quotient rule, so be it. Low d high minus high d low over the square of what's below. Okay. So same as these, except maybe a little easier. Okay, so either way, let's just do an example. So example 1, suppose y is equal to, let's just do sine x over x. Okay. Now we're not taking the limit here, right? Remember the limit as x goes to 0 is 1. We want to take the derivative, right? We want to find the derivative of y. Oh, and I shouldn't even put an arrow here, because that looks like a limit, right? Okay, so find the derivative of y. Right. In other words, we want to take the derivative of sine of x divided by x. Okay, so there's my high, there's my low, right? X is low, sine of x is high. So to take the derivative, low d high minus high d low. So x times the derivative of sine of x minus sine of x times the derivative of x divided by x squared. Okay, now we still have to take the derivatives. So the derivative of sine is cosine minus sine. Be careful you don't take the derivative of sine, right? But you take the derivative of x, which is just 1, divided by x squared. Okay, and that's basically it. I mean, there's not a whole lot we can do to simplify this. So we can just leave it as it is. We could split this up as two separate terms here, right? We could do x cosine x over x squared minus sine of x over x squared. And we can cancel one of these x's here. So this would be cosine of x over x minus sine of x over x squared. But personally, I like leaving it as one big fraction. At that said, I'll accept either. They're both correct, right? Right, let's do another one. Let's take the derivative of, how about x squared minus x over cosine of x. Okay, so this one's a little trickier, but it's the same quotient rule, right? Low d high minus high d low over the square of what's below, right? So low, that means cosine of x comes first. D high, so that means we need to take the derivative of the numerator, that's the high part, minus the high, which is the numerator, x squared minus x, times the derivative of low, that's the cosine of x, and then divided by the square of what's below, so cosine squared. Right, and then the rest is just, well, actually, we still have to take the derivatives here. So there's the denominator squared, right? So we still have cosine of x, and then the derivative of x squared minus x, 2x minus 1, minus x squared minus x, and then the derivative of cosine, negative sine. And that's it, right? That's the derivative. Of course, it's a mess, so the rest is just algebra, right? Let's clean this up a little bit and just, well, let's see. What can we do here? Not much. I'm going to leave this factored as 2x minus 1. The only thing I can see here is to multiply a negative times a negative, right? And that's going to be a positive. So I think I'm going to put the 2x minus 1 in front. Multiply that times cosine of x, and then plus x squared minus x times sine of x, all divided by cosine of x squared, or cosine squared of x. Okay, and I think that's good enough. On the other hand, if you do split this up, here's what you can get. You can get 2x minus 1 times the secant of x plus x squared minus x times secant of x times tangent of x. Okay. And I'll let you figure that out, right? Again, I will accept either in this case, but you should know how to go from one to the other. In particular, right, the book might write the answer this way. And if you get this as your answer, you might think it's wrong. It's not wrong. It's just a different form of the answer. It's, right? It's just what which way you think is more simple is up to you. But the book might think this way is simpler. You might think the way on the left is simpler. But ideally you should know both. Okay. All right. Again, we had no choice but to use the quotient rule here. Let's do another one. Let's take the derivative of, how about 3 over x plus 1? Okay, yep. So we don't need, sines or cosines here. I just did those, right? So, well, same rule, right? Low d high minus high d low. So low d high minus high d low over the square of what's below. Okay. If it helps, right? If that's the way you want to remember it. So the rest, we still have to take the derivatives. So we have x plus 1 times the derivative of 3. The derivative of 3 is 0. Minus 3 times the derivative of x plus 1. The derivative of x plus 1 is just 1 plus 0, which is 1. Right? And then let's not multiply out the denominator. Instead, right, this is 0. Minus 3 is just negative 3. So we have negative 3 divided by x plus 1 squared. And that's good enough. Of course, you can also write this as negative 3 times x plus 1 to the negative 2. And that's okay as well. I think maybe I'll do one or two more. So going back to this first example here, sine x over x, there is a mode of thought. Some people will tell you, don't bother with the quotient rule. Just forget it. It's not worth memorizing, right? It's the low d high. I mean, that's ridiculous, right? So it turns out, yes, you don't need the quotient rule. But I prefer to have it as just one additional piece of information that really does help in most cases. So if I were you, I would learn the quotient rule. That's just me. Okay. So how would you do example 1, for example, without using the quotient rule? So let's go back to example 1. And I think I have just enough space to do it. Right. So maybe I should number all these, right? This is number 3 here. This is number 2. And this was number 1. Okay. So back to number 1. The question was to take the derivative of sine x over x. Right. And we did it already using the quotient rule. So how could you do it without using the quotient rule? And the answer is to use the product rule. And if you're thinking, but this is not a product, it's a quotient. Fair enough, right? Yeah. Oops. This is sine x divided by x. It's a quotient. But a quotient is also a product. You can think of this as sine of x over 1 times 1 over x. And now it's a product. Right? And before we go any further, right, sine x over 1 is just sine of x. And then 1 over x, well, you could write that as with an exponent of x to the negative 1. Okay, so now we just need to take the derivative of, I'll leave it like this, sine of x times x to the negative 1. And now use the product rule. Right? First times the derivative of the second plus second times the derivative of the first. Okay. And what's the derivative of x to the negative 1? Well, it's negative 1 times x to the negative 2. Plus, and then we have x to the negative 1, and the derivative of sine is cosine, right? Ooh, I'm running out of space. Let me see if I can squeeze it in here, right? So the rest is just simplifying, right? This is the derivative, but we can simplify it a little, right? This is negative x to the negative 2 times sine of x plus x to the negative 1 times cosine of x. Right? Or you can, if we put the positive term first, this is cosine of x divided by x minus sine of x divided by x squared. And if you get a common denominator, you get x cosine x minus sine x all over x squared. Right? And I think these are the three different ways we wrote the first, or actually there were only two ways. I don't think we wrote it this way, but obviously I would accept that now too. And back up here, yep, we wrote it both ways. Either way is fine, right? So there you go. Product rule instead of the quotient rule. And you can see, I don't think that exactly saves you a whole lot of work here. It's not that much harder than the way we did it up here, in my opinion. But it's an alternative, right? It's just a different way to do it. Okay? On the other hand, for this example 3 here, this does not make as much sense to do it using the product rule. You can, of course. There's no problem with it, but it's a little bit different. And let me erase it. So we did it using the quotient rule, right? And you can see it's not that bad. So let's see what goes wrong if you try to use the product rule. Okay, so right. So in order to write this as a product, this would be the derivative of 3 times x plus 1 to the negative 1. Right? Because, yeah, the x plus 1 is in the denominator. That's what gets the exponent of negative 1. And here's the problem. We actually don't know enough information yet to take the derivative of x plus 1 to the negative 1. Seems simple enough, right? Seems like just a power rule. The problem is that the x plus 1 inside the parentheses is not just an x. Right? You know how to take the derivative of x to the negative 1. Right? It's just negative 1 x to the negative 2. But do you know how to take the derivative of, let's say 3x squared minus 5x to the negative 1? Right? You might think you do, but this one's a little bit more complicated. So I know that this is just x plus 1 in here instead of 3x squared minus 5x, but it's the same principle. Okay, so yes, you will be able to do this after the next section, but not yet. We're not there yet. Okay? Right, so that's the quotient rule. So we have product rule, we have quotient rule. Make sure you know those. Okay, the next thing in this section has to do with the derivative being another function, right? So we're given a function. Let's say y is a function of x, right? And we want to take the derivative, right? So to get the derivative, we get dy over dx, or f prime of x. Sorry, that's not a 1, that's a prime, right? Okay, and what you get is a function of x. Right? So let's look at an example here. Let's suppose y is just x to the 4 plus 2x squared. Okay, so the derivative of that, well, again, it's the derivative of y, or the derivative of x to the 4th plus 2x squared. And yep, there's no product rule necessary here. There's no, quotient rule necessary. This is, just the sum rule and the power rule, right? And constant times function rule. So we get 4x cubed plus 4x to the 1, right? Okay, so that's the derivative, right? And the derivative is the slope of the tangent line at x, or the instantaneous rate of change of the function. Okay. Right. So, and in other words, if this is my f of x, then this becomes f prime of x. That becomes the derivative. But it's only the first derivative, right? There is something called the second derivative. Right? So the second derivative, right, is just the derivative of the derivative. Right. So in other words, we took the derivative already. We can now take the derivative again. So here's how that's going to go, right? We're going to take the derivative of the derivative. That's supposed to be y, yep. So look what happens. You get d times d is d squared times y, and then dx times dx is just dx squared. And I know there should be parentheses around the dx, but we just don't bother. We know it's dx times dx, right? So that's one way to write it, right? Of course, you can also write it as the derivative of f prime of x, which is going to be f double prime of x. Right? So the double prime means that it's two derivatives, second derivative. Okay, so again, y was originally this, x to the 4th plus 2x squared, and we took the first derivative, right, and we got 4x cubed plus 4x. So what happens if we take the derivative again? So we have to take the derivative of 4x cubed plus 4x. And again, same rule, right? Sum rule, constant times function rule, and power rule. So hopefully by now you're used to this. This is 12x squared plus 4. Okay. So yeah, if this is the first derivative, this is the second derivative, right? So f double prime of x, right? Or, right, d squared y divided by dx squared. Either way. Okay, so that's the idea of the second derivative. Right, let's do another example before we go to the interpretation. Let's find the second derivative of, so how about sine of x? Okay, so this should be pretty easy, right? So y is sine of x, right? So the derivative of y, and if some of you might be wondering, can I just write y prime? After all, if f of x is sine of x, then we usually represent the derivative of as f prime of x, right? So I'm okay with this as long as you're sure you know what the independent variable is. So there's a little bit of an ambiguity here. What do we mean by y prime? Right, so we'll talk about that later, because, you know, what if this is sine of t? Then this would be the derivative with respect to t. What if this is sine of theta? Then this would be the derivative with respect to theta. And so if you just write y prime, we don't know whether the independent variable is x or t or theta. And so yeah, you have to be careful when you use y prime. But at least for now, y prime will represent the derivative with respect to x. So sure, y prime is okay. Anyways, you know this already, right? The derivative of sine is cosine. So what would the second derivative be? So the second derivative of y, or y double prime, again, that's sloppy, but it's okay. So what's the derivative of cosine? It's negative sine, right? So that means the second derivative of sine is just the opposite of sine. Okay. Right. And of course, you can take the third derivative. What would the third derivative be? Well, it would be the derivative of negative sine. The negative is a constant, so that comes in front, and the derivative of sine is cosine. So we just get negative cosine for the third derivative. And then you can take the fourth derivative. So instead of writing all these prime symbols, we usually just use the number 4 here. The problem is this looks like f to the fourth power. So to indicate that it's the fourth derivative, we'll put parentheses around the 4, right? So this is the fourth derivative, not f to the fourth power. So we just take the derivative of the third derivative. The third derivative was negative cosine, and so this is just going to be negative derivative of cosine, but the derivative of cosine is already negative sine. So the opposite of a negative sign is a positive sign. So that's the fourth derivative. This is the third derivative. This is the second derivative. This is the first derivative. And then this is the original function. Now you notice that the fourth derivative is just back to the original function again. Right, so it's the same as f of x. So they just kind of cycle through, right? The fifth derivative would be the same as the first derivative. The sixth derivative would be the same as the second derivative, and so on. Right? And again, that only works with sine. It doesn't work with, say, 4x cubed plus 4x, right? What would the third derivative be here? Y prime or f triple prime? Well, the derivative of 12x squared would be 24x, and the derivative of 4 would be 0. So it would just be 24x plus 0, or just 24x. Okay. Yeah, so, all right, so if that's this, actually, before we go on to the interpretation of the second derivative, I think there's one thing I forgot to do here, and that has to do with the quotient rule. So let's go back to the quotient rule. Yep. So here it is again. I'll use u and v instead of low and high. So v times the derivative of u minus u times the derivative of v. Oh, I wrote it the wrong way, but that's fine. And then divided by v squared. Okay, so some more examples, and in fact, I wouldn't even consider these examples. These are going to be important going forward. So in the last section, we took the derivative of sine and cosine. And we used it many times already, but just as a quick reminder, the derivative of sine is cosine, and the derivative of cosine is negative sine. Okay, so you should know those by now. Okay. But what about the other 4, right? What about the derivative of tangent? Okay, so we skipped that one because we couldn't do it yet, right? We needed the quotient rule. So how do we take the derivative of tangent? Well, we're going to take the derivative of the definition of tangent is that tangent is just sine over cosine. Okay. So we're going to apply the quotient rule where u is sine of x, right, and v is cosine of x. Got it? So applying the quotient rule, we have low d high, so cosine of x times the derivative of sine of x, minus high d low, so sine of x times the derivative of cosine of x, divided by the square of what's below, so cosine of x squared. Now take the derivatives, right? So we get cosine of x in the numerator times the derivative of sine, which is cosine of x, minus sine of x times the derivative of cosine is negative sine, all divided by cosine squared of x. Okay, so far? And that's it. The rest is just simplifying. For one thing, cosine times cosine is cosine squared. And then sine times sine is sine squared. But it's a negative times a negative, so it's actually plus sine squared over cosine squared. So that's looking a little bit better. Now, hopefully you remember what cosine squared plus sine squared is. It's the Pythagorean identity. It's just 1. So this is really 1 over cosine squared. But cosine, 1 over cosine is secant. So this is really secant squared of x. It's a looking box, right? So there's the answer, right? So the derivative of tangent is secant squared. And unless you want to go through all this all over again, you might want to memorize it. It's one that really comes up quite often enough that it's worth memorizing rather than going through this over and over. Okay, so that's tangent. What about cotangent? So the derivative of cotangent, well, you can get that by taking the derivative of cosine over sine. Right, so it's just the reciprocal of what we just did. Rather than go through this again, I'll just give you the answer. Or, it's a good exercise. It's one that you might want to do right now. So hopefully you got either negative 1 over sine squared, but you can also write it as negative cosecant squared of x. Okay. So again, this is another one you probably would want to memorize. The derivative of cotangent is going to be negative cosecant squared. Okay. And finally, we get secant. Right? We can take the derivative of secant by doing 1 over cosine. And this one's probably even easier for you to do. And I forgot what you get when you do it this way. But the way I remember it is it's just secant times tangent. Right? Or it's sine over cosine squared. But trust me that you're going to want to remember it this way rather than sine over cosine squared. Right. So, yeah, let me just write that down. So the derivative of secant is secant times tangent. And, we can forego the parentheses. Secant times tangent. And finally, the derivative of cosecant is negative cosecant times cotangent. So that's all of them, right? So that's all 6 trig functions. And again, all 6 of these you should know, right? Derivative of sine is cosine. Derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. The derivative of secant is secant tangent. And the derivative of cosecant is negative cosecant cotangent. So it may take you a little while to get used to these. One thing that I always remember that helps me remember which of these have a minus sign in front, right? Because some have a minus sign, like derivative of cosine is minus sign, right? And derivative of tangent is positive, secant squared. Derivative of cotangent is also a minus sign. And for cosecant, you also have a minus sign. So notice the connection there. They all have a co in front, right? So cosine, the derivative will be negative. Cotangent, the derivative will be negative. And cosecant, the derivative will be negative. So again, that helps a little bit in figuring out which ones have the negative sign and which ones have the positive sign. The cos have the negative, the non-co functions have the positive. But the rest is up to you. You should know these by heart at some point soon. I mean, again, you can derive them using the quotient rule, but if you have to do this every time you need the derivative of tangent or the derivative of cosecant, you're wasting a lot of time. You probably just want to learn them. Okay. Okay, now we can go on to the next example. So we're given a function x of t, right? So I decided to use x for position rather than s because, well, my s's kind of look like 5s, so I like x better. So, you know, x could just be the position along the x-axis, right? So you're moving sort of back and forth, left and right. Right. So that's the position in feet at time t seconds. So first question is we want to find the velocity at time t equals 3. And because we're only given one time, right, it doesn't say from t equals 2 to t equals 3, right? That would be average velocity. We're given the velocity at time t equals 3 seconds. So again, that means instantaneous velocity, which means the derivative, right? So to find the velocity at any time, we just take the derivative, x prime of t, or dx over dt. And hopefully you can do that in your head now, right? 10t to the fourth minus 6t plus 5. So this will be the velocity at any time t, but we want it specifically for 3 seconds. So now we can plug in t is equal to 3 seconds, right? In fact, we can write it as x prime of 3. And in this format here, how would we represent the 3 seconds? We would put a vertical bar indicating that we're evaluating this at t equals 3. So that's a little awkward. That's why this notation is probably a little bit better. But either way, now we just plug in 3 seconds, right? So 3 to the 4th, sorry about that, minus 6 times 4 plus 5. Oh, not 4, 3 seconds, right? 6 times 3 plus 5. Yes, t is 3. Okay, so 3 to the 4th is 81, and 81 times 10 is 810, minus 18 plus 5. So 810 minus 18 is 792. 792 plus 5 is 797 feet per second. Again, don't take my word for it. Use your calculator if you have to. Yeah, I think that's what I get, 797. Right. And that's actually pretty fast, but that's the nature of this function here. You can get pretty fast even after 3 seconds. Okay, so that's what the derivative represents. In terms of the position, the derivative is the velocity. It's how fast the position is changing, right? So velocity, you write it this way, velocity is the rate of change of position. Right. So every second that goes by, we're moving 797 feet in that 1 second. Well, at least at that moment, right? Later on, we might be moving faster or slower, but at time t equals 3 seconds, we're moving 797 feet per second. And just to illustrate the point here that, yes, our speed will be changing. if we want to find the velocity at t equals 4 seconds, well, now we plug in 4 for t instead of 3. So this will be 10 times 4 to the power 4 minus 6 times 4, that I had that originally, plus 5. Okay, so now you plug that in your calculator, and let's see, this is going to be 4 to the 4 is 256, times 10 is 2560, minus 24 plus 5. And if I did this right, we get a whopping, 2,541 feet per second, which is way faster than 797 feet per second. And so you can see that even after just 1 second, we're already moving quite a bit faster. Right? In other words, our speed is changing, right? The velocity is changing. The velocity is getting bigger. Can't spell velocity. Velocity is changing. Okay? So that means we're moving faster and faster as time goes by. But now we can make this a little more specific here. If velocity is changing, how fast is the velocity changing? In other words, right, what is the rate of change of the velocity? Well, if you want the rate of change of something, what do? We wanted the rate of change of position. We had to take the derivative of position, and that gave us velocity. Now, if we want to take the derivative, if we want to find the rate of change of velocity, we take the derivative of the velocity. So we want to take the derivative of the velocity. Right? So we can write that as dv over dt, or v prime of t. And that's the derivative of the velocity. And in fact, there's a word for the derivative of the velocity. It's called acceleration. So acceleration is just the instantaneous rate of change, i.e. the derivative of the velocity. Okay. Right. So in fact, you can use a of t for acceleration. Okay. Now, I forgot what the velocity was. It was, this thing up here, 10t to the fourth minus 6t plus 5. So just as a reminder, v of t, 10t to the fourth, minus 6 times t plus 5. There we go. Right? So that's the velocity now. That tells us how fast we're going. Now, how fast are we going faster? What is the acceleration? So for that, we need to find the derivative of the velocity. But this is the velocity. To take the derivative, we use the power rule, sum rule, and so on, right? So 4 times 10 is 40. Decrease the exponent by 1. 4 minus 1 is 3. And then minus 6 times the derivative of t is 1. And the derivative of 5 is 0. So we really just get 40 times t cubed minus 6. Right. So this is not the velocity, right? This is the acceleration. It tells us how fast the velocity is getting faster. Okay. So what's the acceleration after 3 seconds? Well, plug in 3, right? So 40 times 3 cubed minus 6. Okay, so 40 times 27 is 1080. Oops, sorry. Didn't mean to do that. 1080 minus 6 is 1074. And what are the units here, right? So if position is in feet, in this example, velocity, right, is feet per second, then the acceleration tells us how fast the velocity is getting faster. It's feet per second, or feet per second squared, right? Because you take 1 over s and you just multiply s times s. So this is going to be in feet per second squared. Okay, so those are the units of acceleration. In other words, right, after 3 seconds, whatever the velocity was after 3 seconds, it was 797, then the next second, you're going to be going about 1,074 feet per second faster. So every second that goes by, this is how fast your speed is increasing. Again, at that instant, right? The derivative is a local thing, right? It only applies very close to that time period, right? That 3 seconds. Okay. Because the fact is the acceleration is also changing, right? You can take the derivative of the acceleration, that would be the third derivative already. Right, so the derivative of the acceleration is the second derivative of the velocity, which is the third derivative of the position. Right, and I forgot to mention this, but the acceleration, of course, is the second derivative of the position. Right. But it's the first derivative of the velocity. So to get the acceleration, given the position, well, you take the first derivative first to find the velocity, then you take the second derivative to find the acceleration. Okay. Yeah, so if I remember right, the word for the third derivative is the jerk. And why is it called the jerk? Because it sort of implies that there's sort of a jerking motion, right? If you go back and forth very quickly, you're kind of jerking back and forth, right? So, yeah, again, I'm not even sure that that's exactly where it came from, but yes, the derivative of acceleration is the amount of jerk. Or to put it another way, and again, this is a little bit of physics, and some of you may or may not have had this already, right? You might remember Newton's second law. Force is mass times acceleration. So if you want to move an object, right, what do you have to do? You have to push it. And if you push it with a force, not only is it going to move, if you're neglecting friction or air resistance, it's going to accelerate. When you push on an object, it's going to move faster and faster and faster, right? In a certain direction, in the direction of the force. Okay, so yeah, if you want to move an object, you push it with a force, it's going to accelerate. Right. So that's Newton's second law. So if you push with a force and then maybe pull it backwards, now your force is changing, and that means the acceleration would be changing. And so if you push forward and then backward, that implies that it's a jerking motion, right? And yes, again, we're not going to see the third or fourth derivatives very often. I mean, you can take the third derivative or fourth derivative just by taking more derivatives. But as a practical matter, usually the first derivative is important because it's the rate of change. The second derivative is also fairly important because it's the rate of change of the rate of change. But then most people have a hard time wrapping their head around what's the rate of change of the rate of change of the rate of change. And that's just something that doesn't come up all too often. So we're not going to deal with jerk or the fourth derivative or the fifth derivative. Okay, so I think that's all there is to this section. We talked about the product rule, the quotient rule, the derivatives of tangent, secant, cotangent, and cosecant, and then what are called higher order derivatives, the derivative of the derivative, or the second derivative. Okay. Oh, you know what? I'll do one more. I think I have just enough time for one more example here. So let's suppose y is, let's actually go back to t, I think. So suppose x is equal to t squared times, I was going to do tangent. Okay, let's do sine of t then. Okay, so t squared times sine t. And we want to find the second derivative of x with respect to t. So you can write x double prime, but be careful, that's not the second derivative of x with respect to x, because in fact that would be 0. It's the second derivative, but with respect to time. So this would be like an acceleration, if you will. Okay. All right. Well, before we can get the second derivative, we can't, I can't go directly from one to the other. Not really. Not in my head, right? So before we get the second derivative, we have to get the first derivative. Right? So we have to get fx prime of t first. And let's just go step by step here, right? This is t squared times sine of t. So what rule do I need here? Okay. Yeah. You need the product rule, right? This is not 2t times cosine t. Please don't make that mistake, right? That's just wrong. You cannot multiply the derivative of t squared times the derivative of sine. Instead, we use the product rule, right? First times the derivative of the second plus second times the derivative of the first. Okay, so, yep, the derivative of sine is cosine. And then the derivative of t squared is 2t. And I'll just pull the 2t in front, if that's okay with you. And we can leave it like that, right? So that's the first derivative. Okay, but that wasn't the question, right? The question was to find the second derivative. So guess what? We got to do this all over again now, right? So now to find the second derivative of x, we have to take the derivative of what we just found, t squared times cosine t plus 2t times sine t. Oh, and I'm running out of space. Okay. Well, that's okay. If I have to clear this, I'll start again. But if I don't write too small, I think I can fit this in here. So what do I need to do here? Well, first of all, this is a sum, right? So I need the sum rule. So this is going to be the derivative of t squared times cosine t plus, and the 2 is a constant, so 2 times the derivative of t times sine of t. Okay. Right, so first things first, the derivative of t squared times cosine t. Well, that's another product rule, right? It's not 2t times negative sine t. It's first times the derivative of cosine, which is negative sine, plus second times the derivative of the first. The derivative of t squared is 2t, right? Now, this plus here, right? Again, the 2 multiplies everything. And this is still a product, so we need the product rule again. First times derivative of second, plus second times the derivative of the first. Now, the derivative of t is just 1, right? Okay, so that's it. The rest is just simplifying. So we get, let's see, negative t squared times sine of t plus 2t times the cosine of t plus another 2t times cosine t, right? Sorry, we're not distributing, just 2t cosine t. And then plus 2 times the sine of t, right, times 1. And I think we're almost done. I think, though, we should simplify these, right? These are like terms. 2t cosine t plus 2t cosine t is 4t cosine t. And in fact, these are also like terms as well, sort of. You can factor out the sine of t. So let me write it this way. We're going to write 2 minus t squared times the sine of t plus 4 times t times the cosine of t. Okay. So you can see that taking the second derivative was a little bit of work here, but that's because we had to apply the product rule, well, once for the first derivative, and then we had to apply it 2 more times to do the second derivative, because there's a product, well, yeah, right. So there's a product here, and there's a product here. So we had to use the product rule here, and then again here. So in total, we had to use the product rule 3 times already. So yeah, you can see that taking second derivatives, in some cases, like in this case here, was pretty easy. But down here, when you have to use the product rule or the quotient rule multiple times, it can be a bit of a nuisance. But you just got to get used to it. There will be several of these in the homework as well. Okay, so that should do it for, I believe, section 2.3, or whatever section we're in. So product rule, quotient rule, and higher order derivatives.